So today we'll talk about the last topic on experimental stress analysis, which is an experiment, a strain gauge experiment. So this particular link will give rise you to this slide, which I will show here from the downloaded one. Okay, let us see what is there. The experiment here is to determine the Young's modulus and Poisson's ratio from a particular experiment. Okay. Actually, the experimental setup is a 4-point bending beam model. Okay. That part we will discuss. So what are the objectives? First is to determine the value of Young's modulus or modulus elasticity from half bridge circuit. Okay. And the second one is to determine Poisson's ratio from a full bridge circuit. So this particular experiment was first carried out, and the report was also made by Mr. Sushanto Guku, who is one of our PhD scholars. Okay. And along with other PG students, postgraduate students, they also took part in this experiment. So the initial part is our introduction to stress and strain analysis, which we all know. Okay, so this part we are not going to discuss here. Okay. So what is the gauge factor, about the gauge resistance, etc. These part are known. So let us see how the experiment was carried out. There are two parts of it. The first part was using a half bridge, where two number of gauges, one on top and the other one on bottom. Okay, so this one on top, this one is bottom, and these two strain gauges, okay, they are oriented along the direction of the stress. These two are considered for the first part of the experiment to determine the Young's modulus. Okay. And in the second part, on both top and bottom surfaces, these two strain gauges are used. So here one is along the direction of stress, other one is transverse to the direction, and for this direction, the strain which this particular strain gauge, transversely oriented strain gauge, it will experience is nu times, that means Poisson's ratio times the axial strain. That much of strain it will experience. So again two such on the bottom, so that gives us 4 number of strain gauges, and by that we created the full bridge and we measured the strain once again. So for a full bridge and in such orientation, what would be the value of strain here? This would be 1.3 times the earlier results. Okay, taking Poisson's ratio as 0.3, or if Poisson's ratio is not known, we will get the ratio of the two measurement, first one without this transverse gauge and the second one with the transverse gauge, and that ratio is proportional to the Poisson's ratio of this material. So this is the principle from which we have measured this Poisson's ratio from full bridge. Okay. And the first experiment gives us the half bridge circuit and gives us Young's modulus from half bridge. That you understand using these two, this one on top, another one on bottom. Okay. Now let us see the experimental setup first. This is the experimental setup. Okay. We have this beam, okay, supported at these 2 points. Okay. So these two are ideally knife edge points. So what we get here is a moment at this point, okay, is basically force applied at the end point multiplied by this overhang length. Okay. And for the purpose of experiment, this beam is kept such that these two lengths L1 and L2, they are identical. Okay. So the moment which is created at this point and at this point, they are identical. And what will happen to the moment between these two support points? They will remain constant, okay, that you understand. So moment diagram is 0 here, getting a particular value of moment here remains constant, then coming back to 0. And our strain gauges, okay, they are fitted somewhere to the middle, or that is not important because moment all through this length is constant. Okay, that you understand. So these two, whatever you can see in this figure, is basically this two. Okay, and there are two other on the bottom side. Okay, the leads, these are the solder tabs of the strain gauge, which you can see from here. Some wires are connected, and for the 4 number of strain gauges we will get 8 such wires. Okay. So these wires are now coming out through this one. Okay. This one contains those wires. Okay. You understand the sealing here, the sealing is applied on these strain gauges. Okay. And also note the other dimensions. Cross section of the specimen is rectangular. Okay, the width and height, they are specified here. Okay, this clear, width and height. The total length is 40 centimeter, that means 400 millimeter. Okay. And so we know what are the distances. Yes. And for the strain gauge, okay, these are the specifications of the strain gauge. See, make the type of strain gauge, okay, following the standard specification notation. Okay. So here it is 350 ohms is the gauge resistance, as you are getting from here. This 10 is the gauge length. Okay. Now this is the test condition for the strain gauge, where this gauge factor 2.1 was observed. Right. Lot number, batch number, not important. And then there is a transfer sensitivity. The temperature compensation value is also given. How much per degree centigrade, it is specified. Now the effect of transfer sensitivity on our experimentation, okay, that is not considered here. Okay. So that part we have not discussed earlier also. What is the effect of this transfer sensitivity? Actually, it requires a correction on the measured strain value. Okay. That part we have not discussed. So this effect we are not considering here. Right. And then you see, these are the strain gauges. They are ultimately connected with a strain indicator. Yes. Where is that strain indicator? This is the strain indicator. Okay. And besides, we have to make other measurements. Okay, measurement for the beam dimension and some other dimension. Okay. So these are measured by using these scales, vernier scale and measuring scale. This is clear. Now this channel strain indicator, this one is a strain indicator which can accommodate the type of bridge, single bridge, that means quarter bridge, half bridge, full bridge, those selectors are there. Okay, this is the display part. The adjusting gauge factor, what it is, that you can adjust here, and all the connectors coming from strain gauges, they are attached at the back end of this strain indicator. Okay, the detailed specification of the strain indicator is here. It is the make, what is the display. This display you can see here. This is the display. Okay. And serial number, measuring range is given up to 2000 microstrate accuracy, and What else?
Number of input means
No. দিচ্ছি দাও একটু পরে দিচ্ছি so number of input means it can take 5 number of strain gauges. Okay, this connectors you are not getting from here, you have to connect it at the other end. So this is for adjusting those gauges actually. Till it is not that you have to attach those strain gauge before taking a reading. We need to balance those strain gauges, right? You know what is zero balancing.
Yes.
So for that, these are the resistance spots for the adjustment of zero balance of those strain gauges. So that you can connect up to 5 number of strain gauges. Input from strain gauges, number of input is 5. Okay. Acceptable bridge configuration, full bridge, half bridge. Okay. Even quarter bridge you can also connect here. Now gauge resistance acceptable 100 ohms to 1000 ohms, and you know that standard values are 120, 350 and 1000. Okay. Operating temperature etc. The other specifications are given. So these are the specifications for the instrumentation part. This part is clear. Let us see the result. So what is there? Now in this figure you identify these knife edges. Okay, this is one, and here we have another one at this point, not clearly visible. Right. And you see at the ends these are the loading arrangement. From this point you see there is a rod which is ultimately attached to a load pan. From this end also there is a load pan. Okay, and on this pan these loads, so these are in step of 500 gram, right? So what are the applied loads? 500 gram to 3.5 kg, right? In steps of 500 grams. So we are getting 7 readings there. And corresponding to half bridge, this is half bridge and this is for full bridge, we get measurement from here. A particular measurement value is also shown here. So these strain readings are here. Is clear? Now what will happen if there is a particular load, say corresponding to 2 kg, we have a sample calculation here. The sample calculation is for how much of load? Bending moment, P is some load for load 1 kg, okay. So for this particular load we have calculated what is the induced bending moment. That we can always find out. If the load is 1 kg, we know this length. So this P into this length is the bending moment, and corresponding to this bending moment, what is the bending stress? My by I, Euler's beam equation. So we know what is the stress value there, right? And the strain reading we are getting from the strain indicator. So what is this strain reading? If we multiply this with Young's modulus, we will get the stress reading.
Yes.
The stress reading is known from this moment value.
Yes.
So we can back calculate what is our E value. So that is what is done. You see, understood? This is bending moment P into L1, and P is in Newton load. So this is mass into G, right? So here you see sigma is this mass is 1 kg into G is 9.81, this mass, and then Y. What is Y? H by 2. This is our height 6.64 millimeter. This by 2, right? So this by 2. This is Y. My by I. What is I? 112 BH cube. That you also know. Okay.
M is nothing but P into L. This one. Zero.
This one is L, right?
Yes.
Right. So this one is L, this particular distance. So PL, this is moment into y, and this is our I value. This is I value.
Yes.
Okay, this is substituted here, and we calculate this is sigma. Okay, in calculation, and sigma is E into epsilon. Epsilon reading is known to us from the table.
Yes, sir.
From the table corresponding to 1 kg, our reading is 92. So if our reading is 92, this is microstrain. Okay. So this by this particular value, okay, this is actually the E value. Okay. So this is the E value we are getting, and what we will get for a full bridge reading, what strain value we will get. This is twice epsilon into 1 plus nu, is it not?
Yes, sir.
Nu is Poisson's ratio. So we have a half bridge reading and we have a full bridge reading corresponding to this 1 kg load, right? Corresponding to 1 kg load, this is our half bridge reading, this is our full bridge reading. So if we compare those two, what we will get? Let us substitute this twice epsilon, that means epsilon h here. So we are getting this relation. So nu is epsilon full bridge divided by epsilon half bridge minus 1. So this is the relation.
Yes.
So from this we will calculate what is the Poisson's ratio. This is what we have done. So all the calculations are done in MatLab. We made a code there, and these are the average values of elasticity modulus and Poisson's ratio. Okay. So that part of the calculation, let us see how this is done. Okay. Let us go into MatLab software. Okay. This is the code. Okay. Understand? This is the function strain gauge experiment. Okay. Length is given. Then this is the moment arm length.
Yes.
This is height and this is width. So it corresponds to these dimensions. Corresponding to these dimensions. Okay. So these are the dimensions, length and other things. And what else we have given? We have these results. Load. We have a vector for load.
Yes,
We have another vector for half bridge strain, for full bridge strain. Okay. Let us see. These things are there in load vector. This is our load vector. Okay. If we calculate how many number of loads are there, length of this P vector is our number of loads. It will come out as 7. Clear? And the corresponding reading, half bridge and full bridge reading, this is also entered corresponding to that observation table, right?
Yes, sir.
Understand. Now what is the calculation? Let's see.
Just a minute.
First is moment,
Yes, sir.
my by I. Actually the moment is this into P, that means G into
Load. Kg.
load in kg
Yes, sir.
into this momentum. This is the moment value, and sigma is this my by I. Clear?
Yes, sir.
So that y value and I value,
Mu.
that value, this is already calculated here, right? This is our I value,
Yes, sir.
112 width into height cube, and this is our y value, the beam height, beam thickness by 2. Okay. So it is getting these values. Now E is this sigma by epsilon. This is E value, modulus of elasticity.
Yes, sir.
So this epsilon value comes from observation, right? So to determine modulus of elasticity, we have used half bridge reading.
Yes.
Okay. So from here we are getting modulus of elasticity, and in the next part we have Poisson's ratio, which is basically the ratio of this full bridge and half bridge reading, -1.
Yes.
Right. So these are the values of elasticity modulus and Poisson's ratio corresponding to each load, corresponding to each observation, right? So what next? A particular value is the average value. So these are the average value. Mean of this E, mean of this Poisson's ratio will give us the average value,
Yes.
right? And then strain is calculated, which is sigma by E. Now which value of E is taking the average value? We will getting this strain, and this is plotted here. The plot sigma strain. So stress strain plot we are generating. So if we run this particular program, okay, this is the plot we will get. So this is the plot we are getting from the observation. This is stress versus strain, and if we want to see what are the individual values, okay, let us do one thing. Let us make it comment, okay. Let us plot the Poisson's ratio value, okay. Let us see how it comes. You see, this is the plot for Poisson's ratio. The value, actually it varies from 0.32 to 0.38, okay. The error is much more for the first reading. For 0.5 kg of reading, the error is quite high, right? Similarly, we can get a plot, individual plot for this E reading also. So instead of sigma versus PR, we can make a plot of sigma versus E, right? This E is our Young's modulus, okay. So this one has to be E as well, right? Okay. Let us see. So you see this is roughly varies from 6.5 to 6.85 into 10 to the power 10, right? So roughly 0.6, it is not, or 600 MPa is the value. 10 to the power 9 is GPa, so this is roughly 68.5 GPa, whatever.
Yes.
So what average value of E we are getting?
66.
This is the value, about 66 GPa. Now, as you understand that this material was aluminium, right? This is aluminium.
Yes.
The figure itself shows that material is quite whitish, okay. It's not a steel specimen, and these are the values for the Poisson's ratio and elastic modulus of aluminium. We take for aluminium, E value is roughly 70 GPa, right? We are getting 66, and Poisson's ratio value is higher than the Poisson's ratio of steel. That is also what we are getting, 0.3. Of course, we haven't carried out any correction on this strain gauge reading. That means we haven't considered the effect of transverse sensitivity that is there, right? So this effect, transverse sensitivity, is there. If we consider this effect, there would be some more improvement in the result. So this is the experiment on strain gauge. Now there are various other way of carrying out the experiment, okay. So these are used in many other applications. So anyway, now you understood how we measure strain actually in a actual experimental setup, okay. So that's all. So this is for our experimental stress analysis, the last part of it. Okay, so let's stop here. Okay.